Hello, welcome to another lecture, and this one is all about hurricanes, so the largest storms on Earth, essentially. So this opening slide shows this big vortex of clouds and spiraling towards the center, and it's actually Hurricane Katrina, the famous one from 2005. And here you can just see the top of the slide in orange, the Gulf Coast. So the Mississippi Delta, New Orleans was tucked behind the Delta, the big city that was devastated back in 2005. So hurricanes can cause huge natural disasters in terms of loss of life, and we're talking billions of dollars worth of, or billions of pounds, whatever currency you're using, worth of damage to an area. And like I say, Hurricane Katrina did that. Hurricane Katrina was the most costliest natural disaster in North American history. It cost, well, the figures vary, but anything between 130 and 160 billion dollars worth of damage was done from that one storm over a couple of days back in 2005. And these hurricanes can cause huge damage and loss of life. Nearly 2,000 people died in Hurricane Katrina. As we'll see, that's quite rare these days, certainly in the United States, because of increased technology in forecasting hurricanes and very good responses to that once you have what we call a hurricane watch and a hurricane warning. There's a hurricane imminent about to strike land. And people evacuate, or you have hurricane shelters, but especially evacuation is obviously very successful. But Hurricane Katrina, sticking with that subject, which I'll come back to, devastated the city of New Orleans, a major city down on the Gulf Coast back in 2005. That's quite unique because of the circumstances that surrounded that event. Basically, New Orleans is defended. It's surrounded by water. It's got the Gulf Coast on one side. There's a river, the Mississippi River. And there's also a large lake just on one bordering the city as well. And it's actually below sea level because when the first settlers there, the first people settling that town and city, it was on marshland. It's still in part of the delta essentially, so wet, saturated ground, and they drained it and built small walls and kept on draining it. And when you drain an area, the soil will compact, becomes less dry, hidden full of that water. And the whole area of the city of New Orleans, most of it has actually something like 10 feet below sea level, about 3 meters below sea level. And so to protect the city, levees were built back in the beginning, right at the start of the 20th century. So these large flood defenses called levees, these often earth embankments, sometimes they have a rock core. Sometimes you can also have different levees which are built out of sort of sheet piling as well. But whatever they're built of, they're there to defend an area from flooding. And in this case, from seawater, both from the river Mississippi, but also from the sea, from storm surges. And these things, storm surges, you can see this big spiraling vortex of Katrina here. It's moving landwards, and as this big low depression, which is what a hurricane really is, it's a center of low pressure. As it moves forward, it literally pushes the ocean, the sea level, up in front of it by many meters or many feet. So it can be 20 feet, or even 20, 25, even 30 feet occasionally, but certainly well over 10 feet. And that will cause coastal flooding. And that's actually what kills most people from hurricanes, is drowning from storm surges especially. And also so this storm surge with Hurricane Katrina overtopped the levees. It was a Category 5 hurricane. So hurricanes are ranked based on wind speed from 1 to 5, 5 being the highest. And I believe we'll come back to what the thresholds are. I think it's something like 160, 155 miles per hour. Above that velocity, wind speed, you're a Category 5, the strongest ones. And that was Hurricane Katrina, a really strong storm and a very large storm surge, a high storm surge. It pushed in front of it. So overtop, but the levees that were built in New Orleans were only built high enough for a Category 3 storm surge. They hadn't been built higher, which is tragic, because they knew in advance that the possibility of a Category 5 was strong possibility, or probability, should we say. But the money wasn't forthcoming, and they hadn't, so they were still category 3, so they were overtopped, and the city flooded. And almost like the analogy, it's like a soup bowl, New Orleans, the city of, and the waters overtopped that levees and flooded the city. It filled up the soup bowl that is New Orleans. And something like 80% of the metropolitan area of New Orleans, 80% was underwater. And that's why so many people died. Nearly 2,000 people lost their lives in that event. Normally they don't. We have hurricanes in the United States, 4 or 5 every year. It's you can sort of count on one hand those who lose their lives, usually when these very large storms come in, because places like Florida, East Carolina, etc., because they're clued up of how to, with warnings and watches, and to evacuate quickly, or to take shelter. There's a lot of public education. We'll come back to all those things later. Spending some time here talking, but I just wanted to mention Katrina a little bit. But yeah, so it filled up, and there were nearly 2,000 deaths. And I might not come back to this point, but Katrina, most of those people, like in all natural disasters usually, were the vulnerable in society. Some people did evacuate. Basically, the call to evacuate that city was put out way too late at the time. A lot of lessons can be learned from that event. And those left behind were the elderly, in old folks' homes, with disabled, the poor, the usual kind of demographic sections of society, unfortunately, who are vulnerable to these sort of things. And they're the ones that mainly lost their lives, which is tragic. And also there were those who felt they were protected. They felt that the levees had been built, the government's looking after them, the local authorities are looking after them, therefore they don't need to worry. They have this protective levee system around them. So the perception of risk was very low. They didn't think they were at risk until it happened. But the crazy thing is that Hurricane Katrina, that they still, here we are, years later, it's still have not been built up to Category 5. It would cost about $3 billion, but I think about $3 or $4 billion to build all the levees up to Category 5 height. It's a huge, it's a huge undertaking. But Hurricane Katrina, the costliest hurricane, natural disaster in U.S. history, cost around about, like I say, up to $160 billion. So 3 versus 160. To me, it seems quite simple. But yeah, all right. We may come back to a little bit on Hurricane Katrina on later slides. Let's go in and learn all about hurricanes. All right. So what we're going to cover is what is a hurricane, and where and how do they form. Hurricane intensity. So how do we measure hurricanes basically on a scale from 1 to 5? And hurricane destruction. We'll be going through the different types that a hurricane can cause, wreak havoc, such as the high wind speeds, such as storm surge, such as inland flooding, regular river flooding. These big vortexes of cloud are, they release their rainfall and cause huge amounts of inland flooding. They carry on over the land and cause a lot of flooding, and a lot of people lose property and lives because of that. Hurricane forecasting. So in terms of long-term forecasting, it's kind of every year. Well, we kind of know that there's a hurricane season you have in the United States, around about 4 or 5 per year. In the Western Pacific, you have about maybe 9 or 10 per year, affecting places like Indonesia and Japan. But on short-term forecasting, basically, when is a hurricane going to touch land, and how strong will it be, and what sort of area of coastline will it affect? So we'll deal with that sort of factors towards the end. And who is at risk? Which areas are at risk, and who certainly are at risk? So some of the usual kind of hazard analysis questions there, but in this case to do with hurricanes. All right, so what is a hurricane? They are the most violent storms on Earth. The rotary cyclonic circulation. So it's this big cyclonic vortex circulation. I should say now in the northern hemisphere, they're counterclockwise or anti-clockwise, counterclockwise in the northern hemisphere. And that's caused by the Coriolis effect, basically the spinning of the planet. And that deflects winds to the right in the northern hemisphere, and you see, and so they spiral down in a counterclockwise manner. Same thing if you let, in the northern hemisphere, water draining down a plug hole, you'll see it does it in that way. In the southern hemisphere, it deflects winds to the left, so they go in a clockwise direction. Okay, all right. So the wind speeds to be a hurricane, so to go over that threshold, going from a tropical storm to a hurricane, it has to be a 74 miles per hour. So sustained winds of 74 miles per hour and above, and you can be classified as a hurricane. Wind speeds can reach up to 185 miles per hour, thereabouts. Huge. There's only one other sort of phenomena on Earth where wind speeds can be faster than that, and that's tornadoes. They can generate very large waves out at sea when the hurricanes are over deeper water, kind of not regular, kind of wind-produced waves. So sort of 50 feet plus waves out at sea, but sometimes actually much more. And then that sometimes we're now starting to see they can actually get up to kind of, we think, from up to, out at sea, up to possibly 90 feet or even 100 feet high or more sea waves. Recently I read up to 130 feet even, caused by these tropical storms, now measured by bottom pressure recorders that measure the height directly of the sea above. Not on land though, that has to be in deep water, but again it shows these very large waves can be caused by these hurricanes. But mostly on average, that's the maximum, generate up to sort of 50-55 feet, sort of the average height of the waves. Okay, so hurricanes, where do they form? Well, they form north and south of the equator, so not actually on the equator itself. They typically form between 5 degrees and 20 degrees latitude, north or south of the equator. So you can see the areas in orange here, areas in which tropical storms form, and they form, and then the tropical storms develop into the stronger thing, which is a hurricane. You can see here on the map here, you can see them forming the hurricanes affecting North America, for example. They track in from around about 5 to sort of 10 degrees north off the African coast and track in westwards across the Caribbean, and then either go up the east coast or across the Gulf of Mexico, sometimes get a bit more power and hit the Gulf Coast. There's other names given. Hurricanes are known as by other names elsewhere in the world. So the ones that affect the Western Pacific are called typhoons. That affect the islands of the Western Pacific, like the Philippines and Japan. The storms that affect the Indian Ocean, affecting the parts of Australia and within the Indian Ocean, are called cyclones. Collectively, the whole lot we can now call, generally in the literature, are called tropical cyclones as a catch-all. So a tropical cyclone is a hurricane, a cyclone, a typhoon. That's a tropical cyclone. All right, but we're going to call them hurricanes now, kind of in the sense of kind of the Atlantic ones. So the recipe for a hurricane, what do you need to create a hurricane, if you will? And there's various factors here on this slide. So the first most important thing you need, you call hurricanes often heat engines. You need warm ocean water, hence why they're formed in the tropics. So you need water in Fahrenheit, around about 80 degrees Fahrenheit or more, which is around about, I think, 27 degrees Celsius or above. And that will provide the energy for evaporation and making lots of evaporation and humid air above that water, for water vapor evaporating. And that evaporated warm water vapor will rise. Warm air always kind of rises, but as it rises, it will become that humid air. The air around it will be sucked in to replace it, because when air rises, you leave an area at sea level of low pressure, and winds always go from high pressure to low pressure. So you very quickly start to get very strong winds moving inwards to this low pressure center. But also what drives that driving air, what we call a heat engine, is once it rises up into the atmosphere air, it cools with altitude, snow on the top of the mountains. So, and this is what forms clouds anywhere. So as your air, a parcel of air rises up into the atmosphere, it cools, and say a cubic meter of air at a lower temperature can hold less water vapor. it quickly gets to 100% humidity, and the water vapor it condenses into water liquid droplets, rain, cloud. So it condenses. And there's a thing that happens when a gas condenses to a liquid, it releases heat. It's called the latent heat of condensation. It's kind of just a physical thing. And that heat also generates buoyant air. So the whole thing is this heat engine, if you will, all sort of driven by the warm water below, though. And you get the winds start to pick up and pick up and pick up, and you start to get a very big spiraling low pressure center developing. Some of that is said in words on this slide. So I said they form in tropical waters. There's a hurricane season. They develop most often in late summer, when warm water temperatures provide the energy and the moisture. The image on the right highlights water temperature. So the orange colors around about sort of in Celsius, around about sort of 27, 28 degrees water. So that this is where hurricanes are forming. They follow the prevailing winds here. The trade winds are called from east to west. So they follow these trade winds, and this warm water sometimes create these big low pressure centers which spiral along this track, and then they hit the Caribbean. And like I said, then they can either go north or across the Gulf. But before you get to a hurricane, you can go through different kind of categories of other storm, depending on the wind speed. So first off, if it's below 38 miles per hour, we call it tropical depression. Then as wind speeds pick up, between 38 and 74 miles per hour, you could call a tropical storm. And these affect the Caribbean a lot every year. And tropical storms in themselves, they're strong winds. They can cause a lot of damage and wreak a lot of havoc to buildings, etc., just from those sort of winds. So to go back to this thing that being a heat engine, so the energy is fueled ultimately by evaporation of warm water at the ocean surface and subsequent condensation in the atmosphere, which releases this heat engine, this latent heat of condensation. So the whole thing is kind of a heat engine, and that drives the rising buoyant air, which drives air to replace that low pressure area below, and you very quickly get very high wind speeds picking up. Like I said, results in very buoyant air, resulting in low pressure surface pressure and more rapid inward flowing winds. And they form these big vortexes. They form the vortex rather than winds just going straight vectors, straight lines to that middle point of the low pressure center. They're deflected to the right. So as they're deflected to the right, they get deflected and then they spiral around. They're constantly being deflected to the right. So that's why you have this vortex. They're gradually getting nearer and nearer to the center of the what's called the eye of the storm. But they form this big counterclockwise or anti-clockwise, also known as vortex. So you can see the same thing happens in the north with water going down a drain, and Hurricane Katrina doing the same thing, money down a drain. Okay, there's some different elements on this slide. So you've got this something called the eye in the middle of the storm, not labeled as the eye wall as well. The next slide is going to kind of go through these different parts of the storm. So the eye wall, so outside of this calm bit in the middle called the eye wall is the rising air near the center. It's a wall of cumulonimbus clouds, these big high rain clouds, and this is where you have the greatest wind speeds on the eye wall itself, and the very heaviest rain. So right in the center, you get this kind of strange place where the wind speed drops almost to zero, and there's almost very little cloud, and it's typically kind of around about 12 miles in diameter. And this is called the eye of the storm, the eye of the hurricane. There's very little precipitation ceases, wind subsides, like I said. The air, instead of rising, buoyant air, it's actually descending. And when air descends, it actually heats by compression. So it's actually quite warm in there as well. And some parts of the storm, I'll come back to this point. When storms, you can actually have both eye walls go over you. So here, some images of some hurricanes. Here's Hurricane Floyd, bigger hurricane, did a lot of havoc back in 1999 in Florida and went up the East Coast. And here you can see this counterclockwise rotation vortex shape of this big vortex. And you can see as well from the size, there's Florida. Florida's a large state. These hurricanes affect a large section of coastlines, not just a very small section that's affected. It's a large swathe of coastline, maybe a couple of 100 miles or more, and then they track northwards or across the Gulf Coast. So if it's northwards, they're going to affect a huge swathe of coastline up the east coast of the United States, for example. Here's looking down at Hurricane Amelia back in 1994. Again, just showing that vortex of cloud counterclockwise, and then there's a bit more break in the cloud here, the eye right in the middle, and the eye wall, the thickest cloud just outside the eye. Lots of data has been collected on different variables of wind speed and temperature. I'm going to show you a few slides now which show that basically a cross section through a hurricane, the structure of the different variables within it, like wind speed. And how we get this data is usually from either aircraft, often military aircraft. For example, in North America, the US Air Force, they're purpose-built these kind of hurricane hunters to actually fly through the storm and measure wind speeds and air pressure, etc., and temperatures as they go. But also they fly kind of above the storm, and they drop lots of these things called sondes, S-O-N-D, or S plural, S-O-N-D-S, these sondes. And they each have a little kind of a parachute on, and they just float down through the storm, and they've got an inbuilt GPS for location, and they're constantly measuring wind speed and air pressure and temperature, so various variables. So if you put them enough of them through a hurricane, you can build up a three-dimensional image of a hurricane. So this one shows the compass direction, which is what's called the azimuthal component of wind. So on the horizontal and wind speeds, and you can see the orange here, or in the eye wall. The strongest winds are definitely in the eye wall, up to kind of 145 miles per hour here. So it's about a Category 4 hurricane in this case for these figures. And you can see, by the way, it's a very large, massive cloud, up to 18 kilometers high here, so into the stratosphere. And here, the blue, the very lowest wind speeds, below 10 miles per hour, is the eye wall, the eye itself, where sort of wind speeds drop to almost zero within the eye. So if you think of this, this rotating mass, and it's moving landward, and here's a record of wind speed from a coastal area of Australia, where when Cyclone Monty went through in 2004 across this area, they had land-based recorders of wind speed and air pressure at this point. So what's happening here over about a 24-hour period? The red line is wind speed in knots, which isn't quite the same as miles per hour. It's a little bit less, I believe. And you can see that wind speed picks up as that storm approaches, and it goes across the coast here. Then it suddenly drops, and at this actual location, the eye itself crosses the instruments, and the wind speed drops to almost zero. But then the other eye wall comes through this location, and the other half of the storm moves across. So the wind speed picks up again to very high speeds and then drops again. Air pressure, and the orange line, that goes down to very low air pressure. To put it in context, sea level average mean air pressure, I think, if I remember right, is 1016 millibars, thereabouts. But you can see here the millibars go down to about 965, which is very, very low atmospheric air pressure there. Which I say, they're very low pressure. That's why the winds are so fast. They're coming in from outside towards this low pressure center in the middle of the hurricane. Here we have the vertical air motion rather than kind of the horizontal. So here you can get these updrafts, wind speeds, and you see again the highest updrafts are up the eye wall, spiral upwards. Temperatures, so very warm in the eye. That's sinking air that falls down the eye itself. So that's where the warm temperatures are, and also above the storm. Here, the much cooler temperatures are below the storm at ground level, below that spiral of why? Because of precipitation. It's raining, and it's kept very cool just below this area. Here, looking down at a Doppler radar image, so now you can see precipitation, and you can see there's a heavy band of rain spiraling around the central, around the eye walls, especially. Very high precipitation levels. Here again is precipitation, but here you can see in sort of rather than looking down in cross section, again you can see that rain being spiraling up through the eye walls, and very low precipitation actually in the eye itself, the eye of the storm. Okay, so when do hurricanes kind of decay? How does a hurricane stop being a hurricane? Well, there's a couple of things which can happen to it. They diminish in intensity whenever they firstly move over cooler ocean water. So you stop that heat engine, and when could that happen? Basically, the northern hemisphere, when they track further north. So, for example, the ones on the east coast of America, they keep tracking further north, and they're finally over cool water, and there's no evaporation. Therefore, that heat engine is cut off. Therefore, the wind speeds start to drop. You start to cease creating that low pressure center, etc. The other way you can do it, move over land. Immediately cut off that heat engine, that evaporation, which creates the buoyant air. So that's the two ways. But the thing about hurricanes, they're still carrying a lot of moisture, so they will still carry on moving over the land. You won't have the storm surge there, and the wind speeds will start to drop, but you still have an awful lot of rainfall. It can cause a lot of inland flooding for many hundreds of miles inland as that storm moves inland. So perfect storm. We're not going to watch that in this lecture. I show that outside of the lecture. Just a film about it. Left that slide in. Okay, so here's an image going back to Hurricane Katrina, late August 2005, when it struck. This was the beginning of hurricane season. We've talked about this in the opening slide. I spent some time talking about it, but here you can see a Doppler radar of this spiraling mass. The hurricane itself actually just veered to the right. So it's the eye was just slightly to the right as it struck the main city. It was just into Category 5, but it could have the wind speeds could have even been faster, and storm surge could have been bigger if it had veered to the left. And that's because the wind speeds, how you do this, this might pick up on another slide, but I'll mention it now. Basically, the whole storm is tracking, say, 50 miles an hour, the whole system to the northwards. Then you have these spiraling vortex of 150 mile per hour winds going around. So on the right-hand limb of the storm, you combine the two. The wind is traveling upwards and around at this point, 150 miles per hour. Then you also add the 50 mile per hour northward movement. So you can make 200 miles per hour, if you will. And that will produce a larger storm surge to the right of the storm. To the left of the storm surge is left because the wind is now going in the opposite direction. It's still very strong, and it kind of counteracts. So the wind speed is actually quite a bit less. So anyway, so always on the right-hand side of the storm is a larger storm surge, certainly in the northern hemisphere as it strikes land. Okay, so that's a Hurricane Katrina. It picked up energy, by the way. It did drop to about Category 3 as it came over the islands of Cuba, etc., and the Caribbean. Then it picked up more moisture and heat as it crossed this large water body of the Gulf of Mexico and went back up to a Category 5 when it struck Hurricane Katrina, the land. Okay, let's go back to another historic, very large hurricane. This caused actually the most deaths in US history. It was the worst natural disaster in US history. I think it's on a table, and I believe it's about 10,000 people died. But it was a place called Galveston on the Texas coast of the Gulf Coast. And Galveston was this town, the city built on, still there, but built on barrier islands, these low linear islands, which are often offshore on the east side of the United States, the Atlantic coast, but also on the Gulf Coast. And people should never build on them when there's hurricanes around, really, but people didn't know that when they did establish towns here, because they're basically very low shifting piles of sand, these barrier islands, and they're only a couple of meters above sea level. So if you have a storm surge, they're quickly overwashed, as the term's used. And the overwash, when basically the storm surge went right across the islands of Galveston, the whole city was washed away, essentially. Back in the year 1900, September 8th, 1900. You can see the aftermath of that, and most of the buildings are completely destroyed. Hence the very large. There were no levees. The very large death toll. Then this table shows the 10 deadliest hurricanes to strike the U.S. mainland between 1900 and, in this case, 2009. And like I say, over 8,000 deaths, may actually been as high as 10 to 12,000 deaths. From the Texas Galveston hurricane of 1900. It was a Category 4 hurricane. Then there are these other hurricanes, most of them Category 4 or occasionally 5. and the year that they struck, and the amount of deaths. So, back in 1928, 2,500 to 3,000 people died in the Florida hurricane. 1833, so people died, nearly 2,000 people died in 2005 from Katrina, etc. When I looked at this table for the first time, it's a textbook table, it quickly popped out when you see these numbers that most of these dates, take out Hurricane Katrina, remember this goes up to 2009 for more than a century, they're all from the very early part of the 20th century. 1900s, 1950, 1909, 1926, 1935, okay, 1957 maybe, but 1928, 1900, apart from Katrina. Katrina's an anomaly there, it sticks out. Why is it different? What's going on here? If this is face-to-face class, I'd ask you that question. Why do you think most of these large kind of death tolls occurred in the early 20th century, the early 1900s? It's because the lack of technology. The forecasting was much, much worse there. Basically, they were reliant on ships coming back to port and saying, hey, there's a storm approach. We didn't have satellite imagery then, etc., and all the communications we have now. Hurricane Katrina is different. It's an anomaly because it was unsuspecting. It was caused by, they thought they were defended by this levee system. The levees were overtopped. The soup bowl filled up. People drowned. That's a sad truth there. So it's very unique in circumstances that caused the devastation, the natural disaster that was Katrina. Next slide shows hurricanes categorized, what's called the Saffir-Simpson scale that ranks hurricanes. The relative intensity of a hurricane from 1 to 5 based on wind speed. So here you can see the different wind speed brackets. So to be a hurricane, you have to be 74 miles per hour, remember? So category 1, 74 to 95, etc. If you're over 155 miles per hour, that's a category 5 hurricane, the strongest. Here's some quite useful information. It shows you the sort of storm surge you would get from these hurricanes. So here, for example, category 5, which is Katrina, it was verging on the category 4 to 5. Most people report it as a category 5. The city itself was around about 20-foot storm surge to the east of the city, the suburbs of the city. Went on that eastern limb of the storm, it went up to something like 28 feet, the storm surge. Hurricane Sandy, I might mention another hurricane which struck the United States. It was only back in 2012. I was living in America then when this happened, and not far away in Maryland. And back in 2012, Hurricane Sandy struck. It tracked up the East Coast and hit land in New Jersey and Long Island up in New York, a long, long way north, where you don't normally get large hurricanes getting that far north. They called it at the time Superstorm Sandy on the news at the time. It wasn't actually a hurricane. It was verging, essentially a tropical storm as far as wind speeds. It's verging on the kind of category 1, but then they dipped below. But the storm surge was around about 6 feet plus a few more feet. I think it was total 9 or 10 feet, because unfortunately it was a very high tide at the same time when it struck. It's what we call spring tide. Every 2 weeks you have these very large tides. So that we made the storm surge even higher then. Hurricane Sandy, though, was actually the second costliest hurricane in US history. Katrina being the most, 130, maybe $160 billion of damage, category 5. Sandy, $68 billion of damage. A huge amount of damage, but for a barely category 1 hurricane. Normally, if this is class face-to-face, I'd ask you, why is that? Why the huge cost in terms of damage? When it's not a huge hurricane? Well, think of New Jersey. It's one, especially northern New Jersey and Atlantic City, etc. It's large towns all the way up that coastline and into Long Island as well. And they were the areas affected. So a lot of damage was, if you basically, it goes back to the definition of a natural disaster and a hazard. You need people and you need infrastructure to cause the damage too, to make it into a natural disaster. So densely populated area caused a lot more damage. Categories of hurricane damage. So you can think of hurricanes in terms of the amount of damage, or the category of types of damage, like wind speed, like storm surge. We'll start with the first one, storm surge. This is a large dome of water, like I've already described, really, that it can be up to about 50 miles wide, which is pushed up in front of the oncoming hurricane and floods the land. So here you can see here storm surge. It's flooding in this diagram here, that kind of the coastal towns it houses. and they can be made higher on a on a high tide, which can be a few feet higher as well, which, if it's unlucky to have a storm surge on a high tide. When storm surges are kind of funneled into things like bays and rivers, for example, up in New York, Sandy, the Hudson River, or any estuary or bay, they get bigger, a bit like tsunami do as well, very much like tsunami, or even tides actually. So you're pushing water into a smaller constricted area. That height of that storm surge will get higher, and it can actually double the height, and cause a lot of flooding in that area within the estuary area. On the bottom right, it mentions what I was talking through before about the wind speed. So have a look at that time maybe later. So here you've got the wind speed direction of the hurricane movement in kilometers per hour, 50 kilometers per hour. Here on the right, if I kind of read out tiny writing, the hurricane movement is a net wind of 225 kilometers per hour from the southwest on the right hand side of the limb, because you've got the wind speed on the right of 175 plus the 50 makes 225. On the left, you've got the hurricane movement equals the net wind speed 125, because basically you take off the 175, the 50 from the 175, and it's less anyway. So look through that image later. So here shows that some of the damage caused by a storm surge. This is from Hurricane Ike back in 2008. I forget which category it was, something like category 3 hurricane, 105 mile per hour winds. And here it struck the Texas coast, not too far from Galveston, but a place called Crystal Beach. And again, here you can definitely see these barrier islands, these low ridges of sand that form offshore. They have a sheltered lagoonal side, the landward side with lagoons and marshes, and then the exposed ocean side on the right in this case. And the winds, you can see the sand as well, we call overwash of sand. It's a natural phenomenon of storms overwashing. But you can see all the buildings, just about every single building in this photograph has been washed away. All you're left behind are these kind of these raft foundations of where buildings once stood. The odd one remarkably stayed up. There was very little people lost their lives here. They evacuated. A warning and went out for people to evacuate, and they did. And people living on this island are well aware of the dangers. There is no levee system. They have to be aware of the danger of a hurricane. They know this could happen, so they all evacuated. But they came back to their homes, and nothing was there essentially. Some of these would have been holiday homes, vacation rentals, etc. But some of these were their homes. So there's a lot of personal tragedies in all natural disasters like that. Other categories of hurricane damage: inland flooding. So all that moisture from the hurricane, once it moves over the land, the wind speeds might drop, but it's going to rain an awful lot. So it causes a lot of rivers burst their banks, floodplains are flooded, towns and areas are flooded on that low-lying areas of rivers, river floodplains, and that can cause excessive damage. It says here from a quote from the guy who was kind of head of the National Hurricane Center, Ed Rappaport. In the last 30 years, inland flooding has been responsible for more than half the deaths associated with tropical cyclones in the United States. So more than half the deaths actually caused by inland flooding of rivers, etc. People being, especially in their cars, trapped in cars and washed away in rivers, for example, caused by this. So here, to related to that driving, here's a kind of a informational kind of poster thing put out by the USGS, US Geological Survey. And it says here at the top, nearly 50% of flooding casualties occur when people attempt to drive through floodwater. So do take note of what it says here. Do not drive through floodwater. So here's a vehicle on the road. Let's say if you had a water depth of 1 foot, there's actually a 500-pound lateral force, still extremely dangerous. That car could be dragged away. If the water is 2 feet deep and you decide foolishly to drive through it, there's then buoyancy on that vehicle. It starts to float, and it can very easily be swept away and then very quickly incorporated into the nearby river and sinks basically and capsize, and it's pretty much fatal when that happens. So the vehicle begins to float, etc. But also, even when it's shallow water, you have to watch out. A lot of that water, it's going through fields, etc. It's full of sediment, and you can't see through it. It's muddy, so you don't see these in roads, these washouts, these big potholes and washouts in the road. So the car can suddenly plow into one of these holes and then again be taken down into the main river, etc. From these floodwaters. So if you ever see any water whatsoever, don't drive through it. It's a key takeaway thing. Other categories of hurricane damage: wind damage. So wind speeds can reach, like I said, 185 miles per hour. They can, that sort of wind speed will blow projectiles, objects through the air at very high velocities, and you don't want to be hit by one. That can be fatal in itself. So you can also cause collapse of buildings. Buildings can be kind of certainly kind of blown down, essentially. Here you can see images of hurricane, bottom right, of Hurricane Andrew back in 1994. A lot of these roofs have been destroyed. Here again in Florida, it's a house being kind of destroyed from the wind speed in this case. And you have to watch out for flying debris as well. Tornado activity, a fourth type of hurricane damage. So you also have small tornadoes being created during these large storms as well. And tornadoes can even have even more intense wind speeds, and they can also cause collapse of structures. Here you can see the velocity that's existent in these hurricane winds. So here you can see a palm tree on the right, and this kind of just plank of wood has literally gone right through the trunk of that tree. So the force needed to do that is huge. And again, one going right through the wall, a branch of a building here, for example, a bit of plywood going through again for the trunk on the bottom here. So again, so it says here at the top, going outside is a bad idea, absolutely. So if you haven't evacuated, stay indoors. If you hurricane shelter if you can, but if not, stay in a basement or the most interior room of your house. Factors that affect the amount of hurricane damage. So various factors. The strength of the storm, most important factor first of all. What sort of category of storm is it? It's based on wind speed. The size and population density of the area affected. I said Hurricane Sandy was a very densely populated area, or is. Therefore, a lot of damage was caused by only a Category 1 hurricane, barely a Category 1. The shape of the ocean bottom near the shore affects the size of storm surges. So especially maybe embayments and constricted kind of estuaries will, as I say, cause a larger storm surge. Also, sometimes shallow water can also pick up the storm surge height. The hurricane risk. So tropical cyclones account for the bulk of natural catastrophe U.S. insurance losses in the United States. And the risk assessment is vital to the insurance industry and to government disaster preparedness programs. And kind of a weird fact, I'm not quite sure why that is, but losses vary roughly as the cube of the maximum wind speed. And there seems to be that correlation. And Hurricane Katrina caused more than 1,300 deaths. It's actually more like 1,800 deaths, over 1,800. I need to change that. And over $150 billion worth of damage. So these large storms can cause an awful lot of damage to a coastline area. How often? So we've talked about hazards and other hazards. The recurrence interval. Think of volcanoes or earthquakes. How often, on average, do they occur? Do they erupt, or does an earthquake take place? You can think of the same thing for a hurricane. Well, generally, hurricanes happen every year. There's some hurricanes. Some oceans there's more. So, for example, the Atlantic Ocean, you have there's 4 or 5 hurricanes form each year, I believe 4, 5, 6. In the Western Pacific, up to 10 hurricanes, or 8 to 10 hurricanes form in the hurricane season. For example, the typhoons there. This shows where they occur, the tracking as well, and all of them you can see that reflected from the reflected to the right as well. This tracking as well. But you can see nicely how they form. Not actually on the equator itself; it's in this area of trade winds, sort of 5 to 20 degrees north and south latitude as well. Hurricane return periods, so recurrence intervals specifically for the southeast part of the United States and the Gulf Coast. So this is the return period in years for Category 3 hurricanes or more, Category 3 or greater. So here, Category 3 are big enough to do major damage as well. So the return periods, these red, well, not always red, these circles with the numbers in. So for example, if I highlight one, the southern tip of Florida, just south of Miami, you've got every 9 years basically, you typically have a Category 3 or more hurricane. So every 9 years there. So it's it's every decade typically you have a large storm. This bit of coastline, and then other areas. So the southern southern Florida, you get these quite rapid return periods. But then other areas like say every 30 years or so. For New Orleans area, you get a Category 3. So they're not common, but they do occur all the way along this coast with some frequency. These large Category 3 hurricanes and more, where they cause a lot of damage. So are hurricanes, talking of frequency, are they becoming more frequent with time? You know, we're going through a period of global warming. Is global warming affecting hurricane frequency? Well, it looks like it's not really. So here's the annual global number of tropical cyclones right around the globe from between the 1970s right through to the early 2000s. And you can see there's some variation, natural variation, but it's pretty much the same. There is no increase or decrease in hurricane frequency, so the numbers each year. But hurricane intensity does seem to be increasing, or is increasing in fact, and we're linking that to higher sea surface temperatures and global warming of recent decades. And that's causing the high sea surface temperatures that are causing the storms when they occur to become more intense. So therefore higher wind speeds and higher category of hurricane. So global frequency or events constant, but intensity is increasing. And the duration is increasing. In other words, they're tracking further northwards in the warmer water as well. A slight diversion of that trend. Frequency does seem to be increasing in the Atlantic as well, slightly though. But globally, it's generally the same. So these sea surface temperatures, this chart generally kind of showing the correlation between storminess, the green line, and blue, the sea surface temperatures. And you can see there's a very strong correlation between. They follow each other, the green and the blue here. So storms, Atlantic storms are green, and sea surface temperatures. So when there's high temperatures in blue, you have very stormy, large storms developing. Again, you can see that there's certainly correlation. So in other words, global warming, there is a correlation with this. So forecasting, how do you forecast, or what sort of things do you forecast for hurricanes? Basically, you're forecasting when it will make landfall, when it will strike, the wind strength you'd like to know, so you can tell people on land what to expect, the width of the affected area, the rainfall amount, and if there is going to be a storm surge. This is all monitored by the US Hurricane Center in North America and parts of the Pacific. But how do you go about doing that? Well, the first thing that goes out, so once you have this data, I'll come back to how you get it, is you put out warnings or watches first and then a warning. So you go through the things you have before a hurricane, the tropical storms, a watch and a warning, then a hurricane watch and a warning. So hurricane watch, I'll read this one out. A hurricane watch is issued for a specified coastal area for which a hurricane or hurricane-related hazard is a possible threat within 36 hours. So it's a possible threat. Hurricane warning is when sustained winds of the hurricane strength winds is expected in a specified coastal area in 24 hours or less. So it's gone from a possible threat to being expected, and that's when you're within the next 24 hours, and that's when it goes up to a warning. And people are very much then, even on the watch, they can evacuate, but a warning very much, it's kind of mandatory, and now they have to evacuate usually. So going back to how you get that data, you use modern technology in recent decades. You use weather satellites, especially, probably the most valuable tool for early hurricane predictions. Limited by their inability to monitor wind speeds and other conditions on the ground, but they do see the vortexes of low pressure centers developing in the North Atlantic, for example, or the Pacific. Specially designed planes flown directly into a hurricane to gather data regarding intensity. So they actually either fly often above a hurricane. If it's a very strong hurricane, they won't really go right through the middle, but they're just above, and then they drop these sons to collect data as well. So they collect it actually from on board the plane, and also from these devices that they let loose to float through the hurricane itself. Doppler radar systems, information about rainfall, wind speed and direction of storms, so land-based radar systems. Out at sea, weather buoys continually monitor the weather conditions, and there's a whole network of them on all coastlines. And computer models help to make predictions about storm tracks. So as the whole thing develops now, very powerful supercomputers, eventually very large computers, can model that development of the storm and help make predictions of which direction it's going to track, etc. So here's just showing some of those images of hurricane aircraft which are measuring. For example, at the back, the one at the back has various radar, etc., to measure various variables, and satellite imagery as well. Some buoys, often fixed to the seabed, but they're again measuring wind speeds, data, air pressure, etc. And modeling. So you have once you get all that data, you can model where you can predict. I'm sure you've seen this on the news channels, where that hurricane will be tracking. And here these different colors relate to the orange at hurricane warning on this bit of coastline. So in this case, kind of Georgia up to North Carolina. And then the wind speeds are going to drop. It says to tropical storm in the blue for warning, for likely, in other words, and tropical storm for possible further north, as far as even as Massachusetts in this case. Who is at risk? Well, this is storms. Every single hurricane between 1886 and 1996, the track of them, and also carries on that track when they basically peter out into just a regular storm, a small storm. So that's why the lines carry all the way across the Atlantic in this case, almost to the British Isles, and inland as well. So basically it shows everywhere on the east coast of North America, for example, and the Gulf Coast is at risk of a hurricane. Certain areas are slightly more at risk. So on the east coast and Gulf Coast, the highest risk are this zone between northern Florida to North Carolina. So that kind of little bit of coastline is at the highest risk of hurricane striking. So it goes through the Florida, Georgia, South Carolina, and North Carolina. And then often they usually veer off into the Atlantic at Cape Hatteras in North Carolina. Then blue, high risk all the way down there across the Gulf Coast as well, and the rest of Florida. Then moderate risk further north as well. Total US hurricane damage by decade. So this shows that for the whole of the US, every decade from the beginning of the 20th century, 1900s. And you can see steadily getting more and more. There seems to be more damage occurring decade by decade. The 2000s, 2000 to 2010, so centered around 2005. Here, 180 billion. This is 10 to the 10, so it's 180 billion dollars worth of damage. Most of that was Hurricane Katrina, but still the trend is upwards. Why? Why is it? I've said they're not becoming more frequent. Why is there more damage? Well, it's all to do with more things to damage. For example, population essentially. So there's more and more people living in Florida. You know, one of the worst hurricane-prone areas. So here's the population of Florida ballooning, going up from, especially from sort of the mid 50s and 60s, steadily increasing or steeply increasing. It was back in early about 1965, only 5 million. Then by sort of 2000, it was up to 15 million, and then predicted for sort of 2030 it could be as high as 30 million. So it's the place to retire. It still is. But they need to be, everyone who moves there needs to be aware of this ever-present danger, or yearly, annual danger of hurricanes. So human interaction with cyclones, tropical cyclones, has increased markedly in the past 4 decades, largely due to population growth, greatest in the coastal areas. And you have to remember, most people live by the coast. So in the United States, about 53% of the United States population live on coastal counties. That's a very high percentage. So it's carrying on this human interaction now, and so urban development in coastal areas, it's increasing development now with population, so it's becoming more and more vulnerable to hurricanes now because of that development. So urbanization of vulnerable coastline increases the magnitude of the effect of cyclones. Destruction of natural defenses, things like sand dunes. So these things have been destructed for development sometimes, or by storms, they're gradually being eroded down. That makes an area more susceptible to hurricane winds. Construction of sea walls and bulkheads, typical coastal defenses, they will actually just deflect large storms, the power of, say, sea waves caused by a storm, and cause a lot of beach erosion. So more storms on a coast will cause actually more erosion, especially as it's deflected back from a defensive seawall, and that beach will quickly disappear. in front of the seawall. Poor building materials and practices can make hurricanes more dangerous to people. So you do have to, the strong, especially the lower category hurricanes, a strongly built building will stand up generally. These coastal areas always usually have to be zoned now because so here you should basically high risk zones nearest the coastline. So here within a high risk zone you can see these properties been washed away from overwash of sediment, etc., and erosion after a hurricane. So here you can see building sort of before and after. So before the top photograph, and then afterwards the right you can see that kind of red roofed building for kind of a point of location. And you can see one of these houses has been pushed off its foundation here into this new inlet, as it says. Another house, the red one's actually been pushed off its foundation, so it's moved off the foundation. So a lot of these houses, are pretty much destroyed from a hurricane here. So how do you minimize the hazard? Well, first of all, we cannot prevent cyclone hazards. We cannot prevent hurricanes occurring, first of all. But primary way to reduce property damage and avoid loss of life is to accurately forecast storms. And we are getting very good at forecasting storms now with modern technology, issuing warnings. So issuing advisories to warn people in their path, a watch and then a warning, and generally making them mandatory so they must evacuate. Other ways to minimize the effects: adjustments to living with the hazard, enforcing building codes and evacuation procedures, having evacuation shelters sometimes as well for those who don't evacuate. Also minimizing the hazard. So residents in areas at risk for cyclones have significant experience, yet do not always perceive the danger. So, a local community in Florida, for example, or South Carolina, they're used to hurricanes, but the perception of hazards depends on your personal experience. So new residents to the area may underestimate the hazard. First of all, they're not used to it. They're not. It's not in their experience of a hurricane. But more experienced people may take the hazard more seriously. They know the strength of a hurricane. They know the kind of damage they can do. But then again, more seasoned people may also take less precautions. They've seen, year on year, you have these kind of low intensity or category 2, 3 hurricanes, and they can live through them. So they become a little bit blasé and they take less precautions. Incorrect predictions may lower the risk perception. So forecasters always have to be aware of that. They try to make the best prediction, but it's meteorology and the study of weather is very complex. So sometimes that prediction doesn't come true. You don't have a category 3 even though it's predicted, and that will lower the risk perception when it happens. Preparations for individuals can take before the hurricane seasons. People should prepare by being aware of the hurricane season when it is. Trimming dead or dying branches, these things which can fly through the air and go through your windows, etc., or the people outside. Buy flood insurance is important. Install heavy-duty shutters. Most properties often have very heavy-duty shutters on their windows to protect the windows and the interior of the house. Learn the evacuation routes and where to go once you get that warning. Very important. Educate and discuss emergency plans with your loved ones, with your family, with your extended family of what to do when a hurricane strikes and you get that warning. Okay, so last slide. In summary, hurricanes are the worst natural disasters that affect the US. Hurricanes are almost perfect heat engines that are feeding off increasing disequilibrium between tropical ocean and atmospheric temperatures caused by the greenhouse effect, essentially global warming. So they're feeding off those increasing sea surface temperatures. They're becoming more intense. And lastly, tropical cyclone intensity and duration are increasing worldwide. The intensity and the duration, in other words, are tracking further in concert with tropical ocean temperatures, again related to global warming. And we will leave it there. All right. Thank you. Thanks, guys.